Hello, welcome to the NMR series of lectures. This is Proton NMR Part 5, and we're going to be looking at the influence of the neighboring electron environment. And so this will give rise to different chemical shifts, which is a key piece of information that we get from the NMR spectra. It tells us what kind of environment each set of protons is in, and so that helps us try to figure out the connectivity of the molecule, okay, putting things in the right place based on maybe a formula, and other information. Okay, so I'll go over just general trends, a general chemical shift table, and then I'll just kind of walk through the main factors that influence chemical shift, and then we'll look at a problem. And so chemical shift is the resonant frequency of the nucleus relative to some standard in a magnetic field. Okay, and it's influenced by the number of other hydrogens attached. It's influenced by electronic environment of the neighboring groups. So whether or not they're electron withdrawing or electron donating will change where the signal shows up along the axis, the chemical shift scale. And it's also influenced highly by ring currents. So I'm going to go through the common effects there. Chemical shift, the chemical shift or position of the peak is dependent on the degree of shielding experienced by the atom. So hydrogens that are in a pretty non-polar non-electron withdrawing environment are going to be more shielded than sets of hydrogens that are near electron withdrawing groups. Okay, the chemical shift or position of the peak is reported as a ppm or on a ppm scale. So the signal delta means chemical shift. And so this is the symbol we use for chemical shift. And we're going to be on a ppm scale, which is parts per million. And so I've just shown the why we call it parts per million, because basically you have the chemical shift of the sample, and that equals the absolute frequency of the sample in hertz minus the absolute frequency of the reference in hertz, divided by the frequency of the system or the instrument, and that's in megahertz. So that's going to put you into a different scale. So you have to multiply by 10 to the 6 to get that reported in parts per million. And so that's downfield from a standard. There's a million-fold difference between the absorbed frequency and the frequency in the spectrophotometer. Okay, that's where you're getting the parts per million scale that we're on. Coupling constants related to this. A coupling constant can be easily calculated from the change in chemical shift between one line and another line of a signal. So if you have a triplet, you can look at the difference between the first two lines in ppm and then multiply it by your magnetic field strength, which is going to be in megahertz. And so that's how you get back into a coupling constant value in hertz. You probably won't be doing that unless you're actually really working with NMR spectra, solving structure and reporting and things like that. So this is just kind of an overview of where you see certain functional groups show up along the different proton NMR, but also similar trends in the carbon NMR spectra. You can see that the scales for the chemical shift are much different in a proton than they are a carbon. Carbon goes all the way up to the 200s, whereas proton, usually you're looking between 0 to 15, somewhere in that range. Rarely do you even get up to 15, okay? 10 is pushing it, 11 is pushing it. So when you have acids and aldehydes, that's about the far extreme to the left as you're going, because those protons are directly on electron withdrawing groups or carbonyls and things like that. So again, here's just a table. You can refer to it as you need. I've got a lot of different functionalities here. One that I think is important to point out and that can be useful is the case for the esters. There's two different structures shown here. So esters, we have two different values. And so let's just distinguish that. If you think about an ester, let me just show an example. I'll use ethyl acetate. If you split the carbonyl up in half, you have the ester side and you have the ketone side of the ester. And so these are going to have a lower chemical shift versus those. Okay, and so these are roughly around 4, these are roughly around 2 ppm. And so when you look at this table here and you look at the entry for esters, that's why you're seeing 2 different values, because you have 2 different type of environments about that carbonyl. You have the ketone side. You know, if you had a ketone, that's where you would see ketones as well. And that's why there's no entry for ketones on this table, is because we kind of already have it here in the ester entry, which I'll just say here, this is kind of the entry for a ketone as well. So the carbon, the alpha carbon, if there's hydrogens for a ketone, that's sort of the range you would see it around 2, 2.1, 2.2. Okay, so a little bit confusing otherwise, but really the table is great here because it has a wide range of different types of functionalities. So allylic, for example, that's the hydrogen on a carbon next to a double bond. Benzylic, again, you can see a benzylic hydrogen. That would be the carbon next to the benzene ring. So that's a benzylic hydrogen. And those are different than your normal CHs. Most of your CHs show up around 1, okay, but not over 1. Those are different, okay? Those are in a different environment. And so you can see the influence that environment has on pulling that chemical shift further to the left, which we call downfield. So that is for your reference. So let's talk about factors now that common deshielding or common shielding factors. So a decrease in the number of geminal hydrogens on the same carbon cause a deshielding effect and a relative downfield shift. And so to the left in the NMR scale. So this is a typical standard that gets used in NMRs, and it kind of helps you set all the other peaks. So this has a 0.00 ppm. And so if you, not always does it get used, but if you were to use TMS, a little bit of it in your sample, along with the compounds of interest, and you find that proton in the NMR and you set it to 0, then it'll set all the others relative to that. And so that's used as a standard. And you can see that this sulfur here, it's the silicon, it's having a shielding effect on the chemical shift of the hydrogens that are on those carbons. But if you now look at methane as our sort of example here, methane has a carbon with 4 hydrogens. And so just the general trend is that's going to be more to the right or more upfield than if you start replacing one of the hydrogens for another carbon. Okay, so as you start to have less hydrogens attached to this carbon we're interested in, as you move from right to left, the chemical shift gets further downfield, higher number. Okay, so downfield, further downfield means a higher ppm value. Okay, further upfield, smaller chemical shift value. And so I've got a little chart down here to kind of show you that as well. Low frequency, lower chemical shift, higher field strength. Okay, so just for your reference. So that's the one trend. One trend is to start removing hydrogens. You're going to start to experience a chemical shift difference. And so we'll see that example in a moment. Okay, so let's look here, let's come back to, yeah. Okay, so common shielding, deshielding effects, you can have increase in electronegativity of the adjacent atom. So halogens are a good example for that. As you move left to right on your periodic table, you're becoming more electronegative. As you go up the periodic table through a column, you become more electronegative. And so one would expect that the carbon these hydrogens are more deshielded because of the fluorine versus less deshielded because of the iodine, because fluorine's more electronegative than I. So you can see the trends here are pretty true. I mean, there's a little bit of overlap here and there, but look, we go from 2 to roughly 3 on the average to 3.5 to 4.5 as we go up the trend line. Okay. Another example here, the carbonyl effect. Because the carbonyl has a polarized C double bond O bond, if you think about the other resonance structure, it puts this carbon next to a carbon that has some delta plus character. And so there's an electron withdrawing feel through that carbonyl of the oxygen. And so there's a pull through resonance that you can feel. Okay, so that's kind of an inductive effect, or it could be a resonance effect depending on how things looked. Okay, but nonetheless, it's a carbonyl effect. And that's why ketones, you see those around 2, not around 1. It's because of the alpha carbon effect. You have that carbonyl next door. Aldehydes have even more of that because the hydrogen is directly on the carbonyl. And so you're putting that hydrogen in a very electron deficient environment, being on that carbon, because the other resonance structure shows that carbon has a lot of delta plus character through the carbonyl. And now look at the chemical shift. It's huge, right? So there's that factor, as well as you have a ring current effect going on with the p orbitals. We'll talk about that. So these are just some other examples. You can see here different environments. They both have oxygens next door, but one's an ester, one's an ether. And so you can see, once again, here's the ketone-like side. Excuse me, this is incorrect. I'm sorry. Oh, wait, so I'm talking about this. And then I'm talking about the chemical shift of these hydrogens. And so you can see I've shaded them the right color. Okay, so this is a label here. It's hard to see on the screen. So let's go ahead and this is the ketone like the alpha H's. And this is the ester like COC. Those ones there. Okay. So you can see the different chemical shift, 2 versus 4. Why? Because you're putting an oxygen next to those sets of hydrogens versus a carbon. Okay. So there's an effect there. Allylic versus benzylic, a slight difference, but benzylic's going to be a little bit more downfield because the benzene ring's a little bit more electron withdrawing than just a simple double bond. It's additive now. So let's say you had a benzylic position, okay, like we had before. So let's look at benzylic position again for that one. Ethylbenzene, that's a benzylic CH2. Let's put an oxygen over here instead of a carbon. And so now you can see that it shifts from roughly 2.5 to now 4.5 roughly, right? So there's additive effects, all right? You can couple these effects together and you can see quite a bit of change in the chemical shift. So benzylic H has moved further downfield due to the adjacent electron withdrawing OH group now in the top case, okay? And so there's more of a deshielding effect. So let's talk about common shift, shielding, deshielding effects for ring currents. So I'm just going to use benzene as sort of the standard example here, and then we'll build from that. And so you're putting an external magnetic field into the system. All right, so that's the direction right now I'm showing it. And if I were to lay benzene flat and draw that, and then think about its p orbitals, because you have this aromatic system, you got this continuous conjugated ring involving p orbitals at every atom. And so what it starts to do is these pi electrons begin to swirl. So I call them swirling pi electrons. And what that does is it leads to its own induced magnetic field, okay? And that induced magnetic field can either oppose the external direction or it can actually reinforce it. And so when you think about what happens here when you start to get these swirling pi electrons, the induced magnetic field is heading in a direction like this. And so as it passes through the hydrogen on the outside of that ring, it's in a direction that's the same as the field here. And so it's reinforced magnetic field that you're feeling. And so results in a highly deshielded proton as a result. And you can see now your chemical shifts are getting to 6 to 7 to 8. So the lines of force shown in blue here of the induced magnetic field reinforce the external magnetic field. And so that's why aromatic CHs have such a downfield chemical shift, is because of this effect. It's called ring current. Double bonds that are not aromatic, so simple alkenes, have a little bit of that effect because you can still get the swirling effect between the p orbitals. And so you can get the induced magnetic field created that once when it passes outside of that sort of plane and hits that hydrogen, it's in a direction that's going to reinforce the external field. So once again, we're nowhere near 1 here. We're now around 4.5 to 6.5 for simple alkenes. Okay, so these would just be sort of non-aromatic double bonds. Okay, so that effect is there. You have another one here, aldehyde. So here's the second effect an aldehyde has to have. Not only is the hydrogen on a carbon that's part of a carbonyl, there's also this swirling effect between the pi electrons within the carbonyl. And so you get the induced magnetic field that passes on the outside through that hydrogen that's in the plane. And it's going to reinforce it even more. And so now we're up into the 9s and 10s. Okay, so that's an additive effect here. You have the carbonyl effect itself, but then you've got the sort of this ring current effect for pi electrons. Now here's one where you get a deshielding effect, and this is terminal alkyne. So I think about a terminal alkyne, and when you get the ring current, the swirling pi electrons around it, it starts to look like a cylindrical can. I call it the donut effect. And if you imagine a pencil through the middle of that, the hydrogen is the tip of the pencil or the eraser. And the lines of force now are going to pass through the middle, and it's going to oppose the external direction. And so you get this huge shielding effect for terminal CHs of an alkyne. Look at the chemical shift now. We're around 2 to 2.5. We're no longer in the 4 to 5 or 7 to 8 or even 9 to 10 range. We've gone back to the upfield range of 2 to 2.5. And so this is a shielding effect that the other ring current systems that I've talked about here don't feel. Okay, so terminal alkynes have a nice shielding effect because of this different type of shape. Okay, the cylindrical shape around the alkyne, like a stack of donuts. Okay, and so it creates a different effect. The lines of force of the induced magnetic field oppose the external field, not reinforce it. And so you get a shielding effect. All right, let's try to put some things together now. Here is from lecture 42, structure D, and we're going to assign then each peak type to the number. So let's go ahead and call that a singlet. That's going to be 3 hydrogens. This will be a singlet, 2 hydrogens. This will be a singlet, 3 hydrogens. Here I have a doublet, 2 hydrogens, another doublet, 2 hydrogen there. And so the question is, which singlet is which? So here we go. We've got a ketone here. And so there's the alpha carbon, right? So those should show up around 2 ppm, give or take a little bit here. Okay, so depending on what else is available or around, here we got a proton that's roughly around 2 or so. And so that looks to be pretty good for peak A. It's close to that 2 mark. So I'm going to go ahead and call that singlet A. The next singlet here, I'm on the other side of the ketone. You can see that's also next to an aromatic ring. So these hydrogens have the C alpha ketone like. So I would expect that to at least be around 2, but now it's also on a benzylic carbon. And so that's going to be an additive effect. And so that's probably going to be closer to the 3.5 to 4 range. So I'm going to go ahead and say that this is B. And I think it's B also because if you look at the singlets here, they're not the same height. One of them has 3 hydrogens making up the singlet. The other one only has 2. And so there's a difference there also maybe. Let's go down to the next singlet C. That's going to be over here. So now you've got the ether-like, which is 3.5 to 3, 3.5 to 4, somewhere in that range, but it's also next to not just the oxygen, but on the other side, you have the electron withdrawing aromatic ring. You could imagine a resonance effect making this even more delta plus. So it brings that closer to 4 most likely. But I would go ahead and venture to say that this singlet is C. And then if you think about the other 2 hydrogens, E and D, one of them is closer to an electron withdrawing carbonyl than the other. So H, the H's next to this carbon are closer to the carbonyl than these hydrogens. Also, if you push in electrons here, you can make that carbon delta minus through resonance. Okay, so those are a little bit more shielded. So these are more shielded. And so they're more upfield. Okay, and so I'm going to predict then that D are our green ones and E are the red ones shown here. Okay, so that kind of completes the structure for D. We've gone ahead, we've analyzed its chemical shifts, we looked at its splitting, we looked at the number of unique signals, and now we tie that into chemical shift, and we can assign the right protons to each peak of choice. If you need to use chemical shift tables, they're there to guide you. They're not always going to show the exact chemical shifts because they're generic tables. Here's the constitutional isomer. So let's go ahead and do the same thing here. If you want to try this on your own, now is a good time to pause your video and do so. Otherwise, I'm going to continue to talk my way through this. Okay. So A, let's look at A and B. This is a great example of when you start removing hydrogens on the carbon and replacing them with other atoms, say like carbon, you start to become more downfield relative to the other. So if you compare this to this, okay, that's a C with 3 hydrogens. This is a C with 2. You can see the subtle change in the chemical shift. And so just knowing that, I predict this one to be furthest to the right and this one to be next door. Okay. Well, you're also becoming closer and closer to what's electron withdrawing. So there's kind of like this electron withdrawing pull through that molecule. All right. So I'd expect the terminal CH3. And I know also by the splitting pattern, right? Look at this. This is a triplet. And I'm going to say that's 3 hydrogens. Okay. It's a triplet because it's next to 2 hydrogens. That's peak B. All right. So there's a relationship there. So let's go ahead and call this A then, and this B. Okay. And then we go to C. C is a triplet. And it's going to be 2 hydrogens, most likely the 2 hydrogens that we get on carbon B. Okay. And so why does carbon B have this complex splitting compared to the triplets? It's because carbon B is adjacent on both sides by carbons with hydrogens, 5 hydrogens total. And so we're getting this sextet. And it's integrating to 2 hydrogens. Okay, so you can see these are all kind of related to each other. This is C here. And then I'm going to draw on the hydrogens here, and I'll put one there, recognizing the other side, it's symmetrical. And so you're going to double up on those. So D is going to be the one that's further away from the aromatic carbonyl. So this will be D, and it's next to right here. So that should be a doublet, and you can see the doublet. So this is a doublet. And that's 2 hydrogens. So I'll write doublet so you don't get confused. And then the next one over is a doublet. Also 2 hydrogens, we'll call that E. And that's closer to the carbonyl. So more electron withdrawing environment puts it further downfield. Okay. Downfield is left, upfield is right. And then we got this peak at 10, and that's the aldehyde CH. Okay. That's on the carbonyl, and you're getting the ring current effect. And so that's a singlet. Not always will aldehydes be singlet. Okay. They can have splitting if this carbon here had hydrogens. Okay. The adjacent carbon has hydrogens. It doesn't. And so that's just a singlet, 1 hydrogen singlet. And if you add up the total number of hydrogens in the integrals, you should have 12 total. Okay. And you should have 12 total because there's 12 hydrogens in the structure. So hopefully that helps you out a little bit, but that's a completely different NMR than our other example here. And those are constitutional isomers, right? They're not completely different, but they're different enough to you know, be completely different in terms of what you see. All right. So they have their own NMR structure basically. So this is back from lecture 44. Let's go ahead and do this also. We can see peak A. We're going to call this A. Typically, you always go from right to left, B, C, D, E, if I did this right, which I didn't. So what did I do here? Okay, I already labeled the structure. So let's label the peaks now. Okay, so A is a triplet. And so you have triplets 3 different places. So we have triplets, one here, here's a triplet, and here's a triplet. And so you'd want to think about where those triplets fall in line. We only have one of these should be a quartet. So let's fix this. So D should be a quartet, not a triplet. So D is kind of helpful because that's the only quartet we have. So we know exactly where to put E or D. So this is D here because that's the quartet. And then you got the triplets on either side of that. Those are going to be either F or E. So I'll go ahead and say F is here and E is here. You can check a chemical shift table to see how close I am. You know, honestly, I don't know if oxygen or chlorine is having a higher effect, but that's something that you can always look up and try to rationalize. Whatever I do, though, I'm going to be consistent in the next 2 peaks for B and C. So if I put E further to the right than F, then I'm going to put B here and C here because C is closer to the chlorine than E. And then lastly, I've got A, the triplet on the end of the chain right here. Okay, so that's next to a CH2 and not in between another chlorine down the way. So I think that would be the right assignment. The rest of the NMR structure is solved. We've got the integrals, we've got the number of different peaks, and we've got the multiplicity. And now we assign the right letters to the right peaks based on chemical shift. And so that kind of completes the cycle for that structure. So I'll let you do this one on your own. Everything should be, you know, very similar. You don't have the real issue and challenge here will be these two, but not really. Okay, so they're both triplets. Everything else are either so far away from each other. This here is a 1, 2, 3. This is the sextet. This is a heptet, so that kind of helps you out. So this one should be pretty easy to assign the letters to the peaks. So I'm going to go ahead and let you do that on your own and move on. Okay, and so I'm going to come back from lecture 41 now. What structure having the formula C11H14O2 shown below is responsible for the spectrum shown? As I mentioned, I would come back to this at the very end here. And so here we are. I'm going to use the molecular formula to my advantage here because I want to decide what SODAR is, the sum of double bonds and rings. And so that's going to allow me to calculate degrees of unsaturation. I call this SODAR. I have a formula. So 11 times 2 is 22, plus 2 would be 24. 24 minus 14 is 10. And divide that by 2 equals 5. Okay, so you have 5 degrees of unsaturation. You have an aromatic region. So 4 of those most likely are going to be knocked out by this benzene ring, where you're going to have 2 different substituents on the ring, X and Y, and X is not equal to Y. Okay, otherwise you'd have one signal in the NMR. And both of these are doublets. And so that means they're splitting each other. And so that's kind of that piece of the NMR. And now the job is just to figure out what X and Y are. I've got an IR structure. So maybe that's an ester. I have 2 oxygens. I don't have a carboxylic acid. I don't have an alcohol. I can't see that in the IR. And I just basically have a bunch of boring CHs otherwise, right? So I have the sp3 CH stretches, and I have the sp2 CH stretches, okay? And then I've got a singlet. I've got a singlet. I've got a triplet, and I've got a triplet. And we have total of 14 hydrogens, okay? And so we're just going to try to figure out what the rest of this stuff is. So I have an ester, perhaps then I have a CH3 on one side. I'm going to take a guess. And it's around 2 ppm, so maybe I have something that resembles, let's do this, a CH3 in the benzylic and a CH3 near the carbonyl place. So I need to have 2 triplets. I'm going to put an oxygen in here and see if that helps. Yeah, so that'll bring one of those around 4 to 4.5 to the ester side. And then on the other side, we're going to have the ketone-like side. And so that gives me at least something I can start working with here. I guessed a little bit. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 carbons. I have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens and 2 oxygens. So I have the right formula. I have the right degrees of unsaturation. Let's see if this makes sense for the structure we're given here in terms of the spectra. Okay, so I'm going to see if I can assign comfortably now the peaks. And I think I can. I think this looks pretty good. All right, so I'm going to call this one here. We can call, let's call that A. And we'll call this one B. And maybe A and B are switched, all right? They're both singlets and they're both 3 hydrogens. And so this is a singlet 3 hydrogen. This is a singlet 3 hydrogen. Okay, they're next to carbons that don't have any hydrogens, so that all looks good. The next peak over would be C. C is a triplet. It's around 3, so it's pretty benzylic-like, but it's got that CH2OH on the other side. But that's very close to being where we'd see a benzylic position right there, which that is. And so that's going to be 2 hydrogens there. a 2-hydrogen triplet. That makes sense. It's next door to a CH2. And then we got D. D's the ester side of that carbonyl. And so those roughly are around 4, but it's also getting close to the aromatic ring. So it's around 4.5 or so, right? So it's a little bit of an additive effect here. And you got, so I'm going to assign this as D. And that's a triplet 2-hydrogen. And then I've got my aromatic hydrogens, okay? One of them's closer to the CH3, one of them's closer to the H. They're pretty close together in terms of chemical shift, mainly because this ester here is starting to get further and further removed from either one of those. And so the effect isn't as strong. And now basically these two groups are becoming more and more identical as that electron withdrawing group gets further and further away from making, you know, basically those two pieces the same. Okay. They're not the same. They have a little bit of difference. Again, there's an effect. So I'm going to say that E then is the one that's closer here to the electron withdrawing ester, and then D is the one that's closer to the CH3 group at the benzylic position. So I think that would complete the problem. That ends the video, and that ends our lessons for NMR. So hopefully these help you, and thank you for your time.